Hello students, let's see the other application of a potentiometer, say to find the internal resistance of a given cell. Internal resistance of a cell stands for the opposition or the resistance shown by its electrolytic solution to the flow of current, which we know already. So using a potentiometer we can calculate the internal resistance. So as the topic related is a long answer time, we may need to design the topics involved or the steps involved, such as say number 1 device, then we must say about the principle of working, then we must detail about the construction, say telling about the parts involved and their purposes with the help of a circuit diagram. In exams, you are supposed to draw labeled circuit diagrams or ray diagrams neatly with pencil and scale. So that is very important. Then first, the way of working. At last, the topics a theory, which includes the whole of equations what we are using to meet the aim. So let us see the steps or the topics one by one. So first about the device, means for a potentiometer. What is it for? Measuring potential difference. Specifically it is for measuring potential difference between the terminals of a cell when it is sending no current. So that is what we say potentiometer measures then an EMF. Say if the cell was sending some current out, then we can measure internal resistance too, which is the basic idea herein. So in short we can say the device measures EMF and internal resistance. So potentiometer is a device which is used to measure EMF, internal resistance, etc. of a given cell. And what about the principle, which says the potential difference to be measured is proportional to the corresponding balancing length. So V proportional to L for a given potentiometer when there is a small and steady current passing through it. So that's a condition, then only we can get V proportional to L. The condition this you have to know very clear. I needs to be small and steady. Current passing through the potentiometer, say from the primary circuit arrangement, must be found small and steady. The reason let us find here. Say V, that is IR. V to be measured, we can write it in terms of Ohm's law, say I into R. R you substitute from its definition as rho L by A, and that bracketed quantity, if that's a constant, then only we can write V proportional to L. In the bracketed quantity which appears a constant here, rho is already a constant, being resistivity of material of the wire, and the wire type we take with uniform area of cross section. And now current also you have to keep as a constant or a steady something, so that I rho by A remains to be constant to make V by L a constant, so that we can always write V proportional to L. So for a steady current only V is found proportional to L. And if you keep I small, then the potentiometer considered will be more sensitive. Sensitive in the sense, if any person is sensitive, you know, the person may be showing more response to a particular some event. More. I mean, if he's short-tempered, so we say he is sensitive. So his response to a particular event will be too much. So here potentiometer also will show more response even for a very small potential difference to be measured. Then we call the potentiometer is sensitive. So more L for a small V. So V by L, say the potential gradient appears very small. So for a sensitive potentiometer you must know the potential gradient, say V by L, remains to be very small. So V by L small means I rho by A must be small. So I rho by A, in that the variable that is the current only. So current can be kept small in order to keep potential gradient to be very small, so your apparatus will be more sensitive. So we must say the principle of potentiometer to be, say the potential difference to be measured is always proportional to the balancing length for a steady and small current passing through the potentiometer. Now see, let's recall the circuit diagram. There's a wooden base with a wooden scale attached at one side. Herein I do alloy wire segment of number 1 only. So 1 meter alloy wire I kept. So AB, the terminals will be at either ways. Then how we could keep a connection? To make you knowing that only I am doing a connection, an arrangement of circuit diagram here with only one wire segment. So primary part let us arrange, which is common in every potentiometer circuit. So as in the previous case, a battery rheostat. Battery is an essential component here. Other components are for doing a support. So rheostat and ammeter are not mandatory, and still if you want to know the amount of current passing, you can keep an ammeter. To vary the current, there is a rheostat. So that is how the primary part or circuit. Now let us look at the secondary part, which will decide for what purpose this potentiometer should be working. So we arranged a cell with non-EMF, say E, or it is not necessary that EMF must be known to us. So one of the cells to its negative galvanometer is connected. Further then connection to jockey runs over the wire AB, and across the cell, say E, we are connecting an external resistance of known value through a key. So when current comes out of the cell in the primary part, it divides at the junction A. So a bit passes through the alloy wire and remaining through the cell 2. In case the galvanometer is not brought to a null deflection. So by the time you start working, make sure jockeys touched over A and B to ensure opposite deflection, so that we can confirm whether potentiometer is working or not. Then let the jockey slide over from the origin, say that is A, to which all the positives are connected. Meanwhile, you locate a position, say J, for which galvanometer shows a null deflection. So length AJ, say L1, could be a balancing length here, which is measuring VAJ, potential difference for the wire portion between A and J, and hence that's for the cell which is connected across A and J too. The cell here is connected between A and J through a galvanometer, which is a passive component only. So we have to know as the wire portion across which only the cell is connected, whatever VAJ is, the same will be for EMF2, say the potential difference of the cell. Why EMF only we are writing here? Because it is not sending current now. So the potential difference measured across the terminals of a cell will be an EMF. That's why we declare VAJ is nothing but E, which is proportional to L1. So E proportional to L1, equation number 1. Now for the second step, what we do means the key K, which is next to external resistance, or you close it so that this external resistance will start drawing a current from the cell connected, say of EMF E. And now again ensure opposite deflections. Then let the jockey start sliding over from the point A. Locate a position J dash at which galvanometer shows null deflection. So we have to know from cell through galvanometer there is no current running, so AJ dash is a balancing length, which is noted to be L2. LAJ dash, that's an L2 here. But this external resistance, as is in a different part, can continue drawing current out of the corresponding cell. So current such as I dash or I2 something, which can be drawn by the external resistance as it is in another closed circuit connected across that particular cell of Em of E. So L2 now here is measuring VA J dash. That's when the cell which is connected across A J dash sending some current out to pass through the external resistance capital R. Now, so is it the same EMF you are measuring or the terminal potential difference? It's not an EMF, instead it's a terminal potential difference only, because this is the potential difference we are measuring between the terminals of a cell by the time a sort of current is drawn from the cell by an external resistance. So even though no current passes through galvanometer, some bit of current passes through capital R from E. So it's only we are measuring, namely terminal potential difference, which only could be written proportional to L2. So now we are measuring V, say terminal potential difference, which should be written proportional to L2. That is our equation number 2. So not an EMF here. So now we'll take a ratio between 1 and 2. Equations 1 and 2. 1 divided by 2. So you make it E by V, that is L1 by L2. So what is E here? The EMF, which was when the key K kept closed. During then there was no current drawn by the external resistance capital R. So the corresponding balancing length L1 to that, we can write the corresponding potential difference between the cells. That's an EMF written as E proportional to L1. And in second time, it was L2 measured for a potential difference between the terminals of a cell when a current is drawn out by an external resistor connected. During then, we have to know the potential involved is terminal potential difference, that is V here. And internal resistance equation, you recall that to be capital R of E minus V minus 1. E by V is a capital R of E by V minus 1. And E by V, instead of that L1 by L2 can be substituted. And capital R is non-T, the non-value of external resistance. So knowing L1, L2, capital R, you can solve for small r, say internal resistance. Thank you.